Danny. I'm from Unity. One of my teams at Unity is essentially given the mission to enable research and development in AI using the Unity engine for that. Yeah. So the key point here is that it's a little less about sort of the machine learning part of it and a little more about enabling various kind of research and development efforts around machine learning. A lot of leading research companies are using us. DeepMind is a very, very big customer of ours. They do a lot of stuff, have a very large team creating environments in Unity and use that to explore new algorithms and models. OpenAI, the AI Institute, Allen Institute, same, and many, many others. The real reason is, of course, that games are really good for AI. Yeah? So board games, a lot of development over the years, it's over 70 years ago with the first chess algorithm. We really like to use game environments. We like to go into video games, which allows us to generate immense amounts of data very, very cheaply to explore different aspects of algorithms. Yeah? So what is it with video games that's so interesting? Why is it that game engine is so interesting for AI research? Yeah? And it's really 4 components. So first of all, first it's the visual component. Yeah? So video games is all about rendering. It's for people. Yeah? So there's a lot of visual rendering taking place that really gives you a very detailed 3D graphical experience. Yeah? There's the physical component. Some of it is what I call Disney physics. You can bounce around, but actually inside a game engine is sort of a real physics engine that's pretty strict, follows the rules of physics. So you have your gravity, you have your inertia, collisions, all of that in games. Yeah? And then you, of course, have the cognitive aspect. In a lot of video games, it's about solving some kind of problem to get the key to unlock the door to the next level or something like that. Yeah? So there are cognitive challenges in there. And finally, the social element. And the social element really comes sort of in the human social element, which is multiplayer gaming, but also in this more artificial or virtual social element, which is that you're acting with one or more NPCs. Yeah? So there's this interaction. It's not static. Yeah? There's a shooter shooting at you. You're shooting back. There's something going on. So bring the game to life. Yeah? So now you have basically visual, the physics, the cognitive, and the social aspect, or the interactive aspect. You have everything that you need to actually explore various aspects of AI or machine learning. Yeah? So in many ways, you can look at a game engine like Unity's as sort of your private biodome where you can explore various aspects of AI. So what I'm going to talk about today is mostly around the work we've done with ML agents, a framework for exploring reinforcement learning. But I just want to say there are 3 open source packages. There's one for perception. So it's basically a package that you can use to generate synthetic data for computer vision systems. So you use the Unity engine to create perfectly labeled visual data, graphical data, that you can train a computer vision system with. Again, you don't go out in the real world and spend a lot of money on labeling data. You just produce, millions and millions of training examples, yeah, at very low cost. We have a robotics package. It's mostly around a URDF importer for robot specifications and ROS and ROS2 support. So it basically allows you to have a piece of robotic software that interact with a virtual robot in Unity using the ROS interface. Yeah? And then finally have ML agents, which is basically an API for using the Unity engine to train reinforcement learning systems. Yeah? So it's all on GitHub. You can snap a picture, go check it out. Very popular stuff. ML agents have over 10,000 monthly active users. We can track that and see that people download and actually install and run training sessions using ML agents. So let's talk a bit about learning scenarios. I know that a lot of you in here are super specialists in reinforcement learning, but I need to make sure that everybody knows what I'm talking about. So very quickly, prime on reinforcement learning is this idea about going in a loop and learning by trial and error. Yeah, I try to say learn by trial and success because that's really what matters. Yeah, and I want to show sort of a little fun game here. We said, can the computer learn? Can a machine learning model learn to have the chicken cross the road safely without getting killed by cars while picking up gift packages? Yeah. And as you will see in this video, which I hope will run. Yeah, no. I have 25 videos, so I hope this one works. This is PowerPoint. Okay. Yeah. I have a laptop with the presentation on. Can we use? No, it's all videos. There are no tone. I'm done with the talking or the text. It's all video. I have an external drive, yeah. There we go. So, rush. Now you see there's a little more animation going on here. Okay. Those. Got this. Let's get to the video. Yeah, so basically you have a reinforcement learning algorithm trying to build a model. It only has 4 functions, left, right, forward, backward for the chicken. And of course, negative reward for getting hit and positive for picking up a gift package. And if you look at the video, you'll see the chicken. Basically, this is very initial, so it's completely random exploration. It's moving in all kinds of directions, but accidentally, in a moment, it will hit a gift package up on the right and then get killed by a car. Yeah. But, you know, after an hour of training, it gets pretty good at it, yeah? So it just figures out how to cross the road, picking up gift packages. You know why we have gift packages in there? To make it move forward, yeah? Because there's more gift packages out in the future. Otherwise, it would just, you know, run around, yeah? So to get it to cross the road. But 6 hours of training, yeah, on a laptop becomes superhuman, yeah? And the cars are coming in randomly, yeah? So it has a generalized policy of avoiding cars and picking up gift packages, yeah? And, you know, I can send cars in as long as I don't let them run faster than then during training, it will always avoid the cars. It will never get killed. Yeah. So we take variations of that algorithm and we do fun stuff like using the physics model to ensure, this is on the physics, yeah, to ensure that the ball stays on top of these cubes. We have these characters, a lot of joints. Anyone who had a little child at home, 12 months old, this is what they try to learn, yeah. Crazy walking, the physics are not accurate enough, the geometry is not accurate enough. It looks a little strange, but you can see it's sort of how we walk. And this example here is about generalizing, yeah. So in this one here, we trained it to walk in shifting terrain, yeah. So it's all about generalization, yeah. Otherwise, this is no good, yeah. So the whole idea is to create something that's generalizable, yeah. Curriculum learning. In Unity, you just create all these instances, and then you start training. And in this case, a very simple example. The little agent, the blue agent, needs to push the cube to a particular position. When it's really good at that, we start making it harder. We put an obstacle in between. It needs to push the cube around the obstacle. This is the point of curriculum learning that we found extremely useful in reinforcement learning. Yes, rather than throwing the baby into the deep water, you start out in the little pool first, and you make it harder and harder. It's so much more efficient, and then you can do things like, using a tool, use the cube to scale the wall, stuff like that. Yeah, so it's a pushing and jumping and doing a lot of different things. Build it up, very, very, very important. Yeah. Another aspect, and these are all sort of single agent examples. In this one here, you should watch. It's important. It's using attention mechanism. You should see what we use reinforcement learning here to improve the agent's ability to focus. So you see the lines are actually ray cast. So it's how it looks. It's the sensor mechanism, yeah. But since this is a virtual sensor, we can reconfigure it. So what the agent learns is to focus on the gap in the wall, pushing the block through. Yeah? I was inspired by working on self-driving vehicles at Uber, where we had 600 sensors. Yeah, half of them looking backwards and the other half looking forwards, and no attention mechanism. Yeah, you had a 3 kilowatt 9-blade server in the trunk processing all this data. But in most cases, why not learning what matters and what does not matter? As in this example, where the agent has learned to only focus on the projectiles that are about to hit it. Yeah? Don't focus on the rest of the world. Just focus on what's coming at you. Yeah? So again, rather than engineering all of this, we use reinforcement learning to figure out what matters and what does not matter. So what it learns is that only projectiles that are coming towards you, they matter. All the other ones, ignore them. Yeah? Which allows this agent to navigate this this threat of projectiles at a minimum computational power. Yeah. So let's jump to multi-agents. Yeah. So all these examples are done with the ML agents framework and the Unity engine. So it's easy to replicate. Yeah. Let's talk about multi-agents. Yeah. Simple collaborative reward here. Just ensure that the ball doesn't touch the floor. So that's the negative reward is if you miss. So they play nicely with each other. Yeah. You can sort of elevate that a bit to a 2-on-2 soccer game. It's very simple. These guys play. You can see some patterns that when one of them is pushing up, another one of them is staying behind. And the way they see the ball and the way they see each other is ray casting. Yeah? So each agent is not a worldview like DeepMind's Atari games or the chicken game. It's not a real a top worldview in pixels. It's just whatever the agent sees using ray casting from its point of view. Yeah. You can elevate that a bit and have a 4-on-4, and you see some very interesting behavior. This is talking a bit about the emergent behavior here, which is that there always seems to be one agent staying behind as a goalie. Yeah? Though the 4 agents on each team are equal. Yeah? There's no definition of a goalie here. There's actually very few rules. There's actually just hit the ball. Yeah? And the positive reward is to score, and the negative reward is to be scored upon. Yeah? And you will see these agents, they will build up this pattern of no matter what we do, they will always end up having someone being the goalie. I want to go back and play it one more time. Let's see. Yeah. You should also notice that no agent is statically a goalie. So if the defensive agent gets the ball and moves up, another agent falls behind and becomes the new goalie. What you have to remember here is, and that's why I showed the little example about attention, is the ray casting is that the agents, they see each other. So when an agent sees that a defensive player move up, apparently that triggers in the policy that someone needs to move back down and be defensive. Yeah? This is the first glimpse of stuff where we look at it and say, well, we didn't ask it to do that. We don't know why it's doing that, but it seems to work really well, which reminds me about DeepMind's work, both on AlphaFold and on Fusion, which they announced earlier today, or was that yesterday? I can't remember. Yeah, where we see behavior that's really useful. It's a great solution to a problem. We have no idea why that is this, what lies behind it. Yeah. So I want to show you a couple of other examples along that path. The agent here is learning to push a single block. That's easy. Yeah. What if we make the block really heavy and we put multiple agents in there, yeah? Now they need to work together. We call this the dance. This is if you look carefully at them, they do some kind of dance before they decide to push a single brick, yeah? That dance is actually a communicative dance. Because of ray casting, they can see each other. They're actually communicating. Again, we have no idea what they're communicating, but somehow they're negotiating which brick, or they're trying to convince. I don't want to put too much, human thinking into this, yeah? But they're trying to vote around, which blocks should we get behind, yeah? Even when they push the blocks, we see different behavior. We see what we call the wedge behavior. Look at them, they are sort of 2 or 3 touching the brick and pushing it, yeah? But we also see stacking behavior where they go behind each other. So again, it's nothing that, you run one training session and you get wedge, and you run another training session and get stack. It's random. There's 2 different ways to solve the problem, yeah? Find that very fascinating. I want to show another example. This is very challenging, just like sparse spaces are very tricky to reinforcement learning. This is another one. This is where one agent actually have to sacrifice itself. One agent will have to die to get the key from the dragon, so one of the other agents can grab the key and leave through the door to the next level or whatever. Yeah? Very interesting problem for reinforcement learning, because reinforcement learning doesn't like when agents die, because then they're sort of out of the game. Yeah? And no agent wants to get out of the game. Yeah? So what we have here is that we actually give rewards to agents after they die, so that if you don't do that, actually in this case, if you just use a normal PPO, they would just wait until the dragon accidentally drops the key or something like that, and then pick it up. Yeah? Nobody would ever sacrifice themselves to get through this. So let's take another example here, dodgeball. So this is a game. You can. This is played from one of the agent's perspective. It's dodgeball. You played that as kids, I hope. Grab the ball, hit the opponent dies. There's another version of this that includes capture the flag that I'm going to show you in a moment. But this is all learned through two teams of Asians playing against each other, learned in reinforcement learning through self-play. Yeah? And I'm going to show you some emergent behavior that comes up here. So number one is home defense. So this is capture the flag. And you should notice that the purple agent out there is basically just defending the flag. It's not moving away. It just keeps defending the flag. And the blue agents are trying to capture that flag. Yeah? So that's called home defense. If you watch enough hours of video of this, yeah, you see there are certain behaviors that repeat themselves over and over. This is one of them, home defense. Yeah? Another one is distract. So the blue agents somehow get the purple agent to leave the home defense, the home base, and leave the flag exposed. Yeah? So you'll see the agents are sort of fooling the purple agent. The blue agents are fooling the purple agents to fall outside so that they can go and grab the flag. We see that as very consistent behavior. Enemy base camping, the purple agent is just hanging out at the destination for the flag capture and just waiting for the blue agent that comes with a stolen flag, and just before that agent can plant it, kills it. So it's just hanging out there, waiting, and boom. You thought you got it, but you didn't. Yeah? And then double teaming. Look at the two blue agents. They just basically keep attacking that purple agent and just keeps it locked in. We see that behavior over and over. Yeah? And then defend the carrier. One purple agent is trying to get the flag out of there. The other purple agent is trying to keep the blue guys away. We also see that all the time. Yeah? And patience. That is an interesting one. It's just the blue agent got the flag, but it's just basically just writing it out until it can safely plant it. Yeah? So it's not rushing to plant it at great risk. It's just writing it out, waiting for the right moment. Play it safe. And then speed run. Keep an eye on this one. It's like it gets the flag, and then it runs really fast with that across the field. Yet another, there it goes. Another piece, you know, when there's a lot of stuff going on somewhere else, it just runs with the flag very fast. Yeah? So I just want to show you all these examples because single agent is really cool. Multi-agent is like 10x cooler. But the problem is a lot of what we see, we have a very hard time understanding. It solves a problem. There are certain recognizable behaviors in there that you only notice those after studying these videos for hours. You see some patterns. And that is clearly something that's worth researching. I'm going to talk a bit more about that. It's all about the data, yeah? I've been in this space for way too long, and what I notice is that we have our own Moore's law, which is that our training data seems to double, you know, every 18 months. Just like density of chips just goes up. We just look at, you know, megabytes were cool, gigabytes now, terabytes, petabytes, just goes up, and the model gets bigger. The models get bigger and bigger, and we really need this kind of synthetic data. We need game engines to produce very cheap data for us. I think that you can imagine how you can just accelerate this. Yeah, we have Unity instances with up to 64 GPUs to accelerate the data generation. So you can do a lot of reinforcement learning with GPUs generating the data, GPUs training models, etc. And you can do that at massive scale. Yeah. We have users that use Unity to generate literally trillions of these frames. Single frames, yes, trillions of those every 24 hours. Yeah. So you can use it to interesting stuff like this, training robots of various kinds. You can use it, of course, to generate training data This is a vehicle simulator built by LG to produce training data for autonomous vehicle training, where you have, I don't know if you can see that, but you have sort of depth information and segmentation and RGB and infrared, etc. Yeah? So I want to finish up here by just highlighting the fact that we have these basic interactions. The agent can have physics, they can collide, they can push things, they have inertia, stuff like that. And then we start putting that into more complex systems. Yeah? And we see interactions happening that we do not necessarily understand. We take that to a higher level and try to draw some conclusions from that, and then we iterate. This is, to me, sort of the framework of multi-agent systems going forward. To me, it was a dream just to have agents play soccer together or do capture the flag, but it's not very satisfying if we don't understand the behavior that comes out of it. Yeah? So I think it's great that AlphaFold can fold protein. I think it's great that these agents can do capture the flag, but it really bothers me when they just solve the problem and I don't understand how. Because we have a long history as humans to develop theories, and that gives understanding. What I see right now is sort of glimpses of a post-theory world where, look, my deep learned algorithm can control fusion. Isn't it great? I have no idea what's going on, but it really works. Yeah? So I think it's important to use simulation to start understanding, to peel that next layer off and understand these emergent behaviors. We have two papers, one of the ML agents and one on an algorithm for multi-agent systems that performs better than most. We are primarily enabling AI research. We also do a little algorithmic research ourselves, of course, but think of this as an enablement tool. Yeah? And one more time, the repositories, snap a picture if you want, but that's where all the software is available. And with that, I think I finished on time. Yeah?